go on record now. Okay, so we're in recording because I do want to post this, and a big part of supply chain and operations and such is based on the fact that most of these processes follow a distribution that's a normal distribution. And I keep repeating the basics because sometimes it takes a few times to hear such things. So mainly tonight, I'm using my touchpad on my laptop to draw with. So I don't know how good it's going to be. I'll try to draw in here. I don't know how good it's ever anyway when I'm using the pen. Trying to find my cursor here. Okay. So the things that we're going to go over here tonight are statistical process control, how it relates to Six Sigma. Okay. And the whole idea between quality control and measuring things comes from Deming, who he's from the United States, but he wasn't really getting a great audience here. He couldn't, and he had powerful things to say about industry, and mainly around our automotive industry, and maybe large items like, household, appliances and things like that, high ticket items and whatever. The quality was really beginning to slip. And Deming actually went to Japan, and he became a demigod over there. If you read his history, he passed away within the last 10 to 15 years. So he's relatively contemporary, and the whole world of quality pretty much focuses on him, although there's other names involved, like Crosby is a big one. Each of them kind of picked up on a different aspect of it. But Deming works with Motorola, although that's a US company. And Motorola really got into the Six Sigma. I mentioned it last class when we were all gathered together. And I'm keeping an eye on the chat items there. If anything, if it's the sound or a question or whatever else, if you have a mic and you want to ask a question, just chime in, get my attention through the mic or whatever, right? Okay. But to do operations, is the core of it is to know statistical process control. And I'm going to go over that relatively quickly. If we have some readings about the weight of a motorcycle helmet, I'm repeating myself, we could have a list of however many samples that we get, okay? So we have a list of samples, and the samples are going to have an ID, right? So basically, when you collect information, you're going to have a recording, some ID of whatever the sample number was, and it could be timed at intervals, exact intervals, or it could be very random in intervals. It could be in time, it could be in quantity. Okay, so you might sample every 50th item or 500th item, and they might come in at different times, or you might sample the one in front of you at every minute. Okay, so you have to think about some of the variability or the choices that you have when you do sampling. And so you have an ID, which is written really badly here. I'm using my finger drawing on this pad, so it's not going to be really super perfect. You have to go by what I'm saying here. So you have an ID, from one through whatever you have, okay, however many readings you have, and then they have some value, okay? And we knew that we could take the mean, okay? So we could take the expected value, okay, the expected value, the EV, the mean, or the average are all the same thing, okay? And then once we had the mean, okay, so once we have the mean, if we have a process that's normally distributed, which many of the processes are, so many of them that it's become its own science, which we're learning here. And when I draw a curve like that, assume it's the ideal one, not the distorted one that I'm drawing. I can actually draw here. So if we have the readings, we go from a pure list that was taken over, let's say, time, okay? So we read, we'll assume that this is by time. And every so often we take a reading. And what we do is once we get thousands of these readings, we count how often they happen, okay? So our readings are on this x-axis of our outcome distribution or probability distribution, we call it, right? And it says for any value of x, which is a reading, we're going to take this reading, right? For any value of x, how many of those did we get? That's the height of the curve there. We're counting things. So this is a frequency diagram, okay? And the middle is the average, is the mean, okay? So EV, try to draw that in there, EV, right? Expected value is right in the middle of this. Oh boy, this is really not fun. Okay, so we have expected value right down the middle, and if we have pretty good normally distributed data, it's symmetric on either side of this. We take advantage of that all the time, okay? That in ideal data, and even when it's not ideal, it's actual data, and it's slightly skewed, Kurtosis doesn't affect it so much, but skew will, all right? Okay, is that when we get these readings that most of the events happen around the mean. We have the highest number of outcomes at the mean or around the mean, and then it diminishes, and the rate at which it diminishes as you get a distance from the mean, at first it's tapering off here. As we come down and x is just a little bit less than the expected value, the slope of this curve here is telling you how fast it's diminishing. And it says, you know, points within from here to here are diminishing at somewhat of some rate. But then when you go between this upper mark here and this other mark here, look how fast it tapers off. For the same distance we go away from the expected value, it drops a lot more. See, it's dropping something like that. You know, in a distance of this far, on the steep part of the curve, all we did was move in the x direction, but we got a big y change. And the frequency is dropping off fast, okay? So I really dwell on just this distribution at all so that you can see what you really need to do is push around on the numbers. This, in fact, doesn't really come naturally. It's something you have to think about what's going on in the different parts of the curve here. And it says that most things that are very close to the mean are going to happen with a high frequency. It's central tendency theorem that we call it. Okay. So then when we got the expected value, we came up with another mean. So the expected value is the mean, right? We came up with the average of the numbers, and then we said, what's the average distance to the mean of each point, and take that average. So it's an average distance to the mean. Okay, so for each of the points over here that we took, 1 through whatever, 1,000, I'm going to write it in as 1K. There's been 1,000 readings here, all right? For 1,000 of these readings, we're going to see how far away it is from the mean, and we're going to take the average. And, oh boy, this is going to be a challenge. Okay, so what we did is we said point of interest, whatever point on x of I, point of interest, from I is equal to 1 to n, okay, for all the points. And by the way, tonight's conversation, there's a slight difference between doing calculations for populations and doing calculations for samples. We're focusing on the population tonight, right? What happens is when you go to do a sample, when you start looking at the math behind that, you lose a degree of freedom, we say. But everything we're going to do tonight is with the population. We're not going to lose a degree of freedom. It's a slightly different function, okay? So now for probably the third or fourth time, you know, I'm mentioning that what we do is we take every point and we see how far away it is from the mean. We subtract the distance, you know, point x minus whatever the average was, and we take that, okay? And we take the average of that. It's just all those over n, okay? And very briefly to retrace, you know, first we said, if you don't do something about modifying the distances, you have, for every point on the left of the mean, you have a point on the right, equal distance, that negates it when you do the sum of all those distances. Some are negative, some are positive. So we thought about maybe using the absolute value, and that doesn't work. According to mathematicians that want to pursue this further, they want to develop a math that works. So we're going to get rid of those absolute values, and what we do is we square that, okay? And if you're keeping track of what the units are for this, let's say that this is in pounds, remember, okay? It could be ounces or something like that, or you know, kilogram or centigrams or something like that, okay? It's a weight, okay? What ends up happening is when you square a number, you're going to get this funny dimension of pounds squared or kilograms squared, which is kind of a strange number. You tend to want to work in things that the human brain can deal with. So to bring it all back home again, and remember, n is dimensionless. It's just some number of things. And so it would look initially like you would take the square root of all that and divide by n, but the way it is defined so that the math continues to build is you're taking the square root of all of that. So I repeat that, especially under recording here, because that's the story about why the intent, the interest that we originally had was a number that just told us what's the average distance to the mean of all the points. And then the mathematician said, hold on to that thought, that's good, but if you can hold it in your brains and deal with it, then we have to contort it a little bit so that we can expand the math. The math is even more useful if we go by this. And if we understand what the compromises are by doing this, we can live with them, okay? So that's where we get standard deviation from. So the standard deviation is the average distance to the mean of all the points, with the complication of squaring each of the distance and then taking the square root of all of that, okay? But I want to make sure you understand what the motivation was. It was a very natural human interest in this. It was a concoction, or it was contrived as a property of numbers that helps us, look at numbers, control them, and understand, for one thing, processes. It's used everywhere in biology, sociology, everywhere else, okay? So we have the standard deviation is just the average distance to the mean of all the points. You just have to remember that there's a square and a square root involved with that. Okay. Now, what is the z? That's where we ended last week. We sort of ran out of calories at the end of last week. What is a z? Okay, why do we use z? Well, we might have a graph here that is the x-axis is in pounds. Okay, so it has a dimension. And what we found is, I'm trying to write in cursive pounds there, but it's not really working. So that's in pounds. But what we did is we normalized the information of this curve so that all disciplines can use it. What we did is we remove the native units, okay? The natural units involved with our interest is pounds, and if you were looking at like a biology experiment, it might be microbes per square millimeter or something like that, okay? And the way that we do that really, really fast is, if you remember, we have this thing called a z, okay? And a z is just going to be, it's totally in terms of the fact that we have for some reason it's not drawing anymore. Okay, so we have this. I'm redrawing a normal distribution like this. And a z has the concept of, we're always looking at a particular point of interest. It kind of looks like what we did for the standard deviation. It bears a little bit of resemblance. But what it is now is we say, how far away is our point of interest from the mean, okay? And then, so I'm going to actually subtract that. That's a minus, okay? So that's a minus. So we're going to take the value of some point of interest, like we were using, I think, I don't know what it was. Let's call it 4 pounds for the average weight of a motorcycle helmet. Excuse me. And we want to know, what's the probability that a motorcycle helmet ends up being 3.8 pounds or less? Or another way, you have to be very careful how you say this. And you might say, what's the probability the weight of a motorcycle helmet does not exceed 3.8? It could be anything up to and including 3.8, okay? All right, so this is the real question we have in life, is what's the probability of that happening? That's the question that we're trying to answer, all right? So we take x minus some point like 3.8, whatever point of interest, it could be 3.2, whatever it might be, and we look at how far away is that point from x, and then we go back and we compare it to how big is that compared to a sigma, okay? So the equation for this is x is equal to your point of interest, x of I. How far away is it from the mean? In terms of, we're going to compare that distance with another distance. Don't get bamboozled by the standard deviation. It's in native units because it's the average distance to mean of whatever unit that you're in, okay? So get it? We're looking at, it could be that our point of interest is like 2 standard deviations lower than x, all right? And so that x of interest minus the mean would be minus 2 sigma. So minus 2 sigma over sigma is minus 2. So z would be is equal to minus 2, okay? Now, there's a formula. There's actually a complex formula that the curve of the standard deviation is well known, and there's a formula for this that tells us that if you give me an x, some value in terms of standard deviations, not in native units, but in standard deviations, if you give me some point there, I can tell you what the probability up to and including that reading is. That's what the z is used for, Okay, so I encourage you to ask questions as we're going on. I keep eyeballing over to the left or to the right here to see if anybody's asking any questions, but I really want you to get this because we're going to build on that. What time is it already? So quarter of 7. Just checking our time on here. Okay, so then if we go to a table out on the internet, if I go search for a table for Z table, you'll find these in a couple of different flavors, but they all pretty much do the same thing. So Z table, if you just do that and you look for images, right? I'm going to pick one. This is just a blur. Let's just see what we've come up with here. This works. Okay, so let's take a look at this one. I clicked something I shouldn't have clicked. What did it do? We go back. All right, so if you can read this, Z is in, this is a negative Z table. It's just showing us the negative values. What does that mean? Let me shoot back over here, okay? Get this out. Okay, so anytime your point, I'm just using this for description here, this normal distribution that I'm showing here. Okay, anytime you're down below, you're looking at a point below the average, your distance is going to be negative here. It's going to be your point, whatever point you're interested in, minus the value of the mean. The mean is going to be larger. Notice it's going to be larger over here. All right. All right. And so when we do is we use the negative Z table for anything on the left-hand side compared to the mean. All your numbers down here are going to be, your Z is going to be negative. You're taking this distance and you're comparing it to whatever your standard deviation was. Your standard deviation becomes sort of a yardstick, okay? So this is what I'm caught up to is where we ended last week, and I had to clarify because I was using an ad hoc example and I sort of got into the numbers. I didn't want to lose everybody. It was extemporaneous and it was beginning to, I think it was bogging down with lack of calories and such, all right? Okay, I'm gonna keep that up there somewhere, all right? So when we go in our table, we're gonna see -2 sigma, right? And then you have to use the horizontal scale, and this table goes to 2 decimal places, right? Yeah, 2 decimal places. So we come in here with -2.0, that's this column right here, -2.01 would be this column, -2.02 would be this. See, so you take this number here and you add it. You got to think in which direction they're going here, okay? One of the anchor points for a table like this is just let's take a look at Z equals 0, okay? When does Z equal 0? That means we have some point that when we compare it to the mean, it is the mean. We happen to have some sample that is the mean, and the distance is 0, so 0 divided by the yardstick or the standard deviation is 0, and we come up with this table is filled with probabilities, okay, that range from 0.000 many ones up to 0.5, okay? So the probability is 50% or 0.5 at the 0 mark, and we use that for an anchor because we said that this was symmetric, that the normal distribution is symmetric, and we say that the total area underneath the curve is equal to 1, okay? 1.0. So that means, what are we saying by that? That means that the probability of anything happen is 100%. Sorry, that looks so bad. Let me try drawing a smaller 0 here. All right. So we said any point from -infinity to infinity, what's the probability? It's going to be 100% or 1. We can talk in terms of like a decimal probability or percent. We can convert it to percent. Okay, so far so good. Say something if you're in that, anxious or need clarification or whatever. Okay, so that's what the Z is, and the description of what the standard deviation is should help us. I'm going to give you try to do this quickly, a quick description. Just move this off here to the side. What are we doing when we use the Z score or we use the Z equation, okay? What it says is we have this scale, Okay, we mark 0 on the scale here. And then we have something we're measuring, like the weight of motorcycle helmets, right? And we put 4.0 as our mean there, okay? All right. What the Z equation is actually doing is if you apply it to the entire, all the numbers of our normal distribution here, what this says is it's like taking all the points and subtracting the mean from it. So it does two things. This equation translates, that's what the minus means. We're translating the data in some direction on the X curve, okay? And by taking your point and subtracting the mean, if we did that for all of the points on here, right? What would end up happening is we would take all the points would end up down here. So the first part of the equation where we subtract X, all right, we end up with what we're showing here, is that we've moved this thing all the way down here, okay? And then and this is still in native units, okay? Right? So we might have some points out here that are, 2.1 pounds. So we subtracted 1.9 from, this would be minus, and this would be 2.1. Equal distance on the other side would be 2.1, okay? And then what we do, so the first thing is that we took all the points, we subtracted the mean from them. This is what you end up with, 0 in the middle, and it still has the spread that we originally had. But what we do is then we scale it. So we translate it, we move it, in other words. Translate means move it. We moved it down so the center is centered over 0. And then we scale it. Everything we in here is we scale it to sigma, okay? So if we look at motorcycle helmets, the standard deviation, or the average distance to the mean, always remember that, to hold on to like a physical value or a physical dimension of why we're even using the standard deviation, all right, is now what we do, the clever mathematicians, they take all the points and they divide by sigma. So when let's say we had today, this motorcycle helmet that we had a 4.0 average weight on it, all right? And let's say the average that the motorcycle helmets differ from 4 pounds is 0.1 pound on average, okay? This is going to be our standard deviation, is 0.1 pound, all right? So sigma is equal to 0.1 pound, all right? So now when we look at what happens when we divide by sigma, what happens there? It says the point on our curve that in natural units is 3.9 pounds, that's 3.9, right? We're down 1 standard deviation, okay? 3.9 minus 4.0 is minus 0.1, right? So we would be taking 0.1 and dividing it. See, we're comparing that measurement to the standard deviation, which is 0.1, all right? So this is 1 standard deviation below the mean, okay? So this is all being recorded. You can go back to this. But that's where the Z world, when we get to Z, we've translated it with this arrow down, and then we scale it, pinch it width-wise and height-wise, okay? And we start talking about it in terms of how many standard deviations we're using rather than the native units. Why do we do this? Because with that one Z table, all disciplines can use this process that we're using, and you only have to publish one Z table, okay? And that's what a Z is. The Z is how far are we away from the mean compared to the standard deviation. It's that simple. I don't want to in fact, what I'm trying to do is simplify it so how you understand it. It's just how many deviations that point is rather than in the native units. Okay, so let's see in Excel how you go about using that, all right? Okay. So I'm going to use this information that we have, that the average weight of the helmet's 4, and we've just pre-calculated that the standard deviation is 0.1 pound, okay? So we're going to ask a question. I'm going to grab a different color here, all right? So what's the probability? I'm going to draw it kind of curvy so it stands out here. What's the probability that the helmets that we produce are less than or equal to 3.9 pounds, okay? Right. How many of our helmets are made to the left or less than 3.9, all right? So when we go to the Z table now, instead of -2, it's going to be -1, all right? See? So 3.9 minus 4 is -0.1. That's this right here. And when we compare it to sigma is equal to 1.1 pound, that comes out that this mark, this point of interest, this X that we're interested in right here, is Z is equal to -1 or 1 standard deviation less than 0. We come in here, here's -1, and we're using very round numbers right now, so it's -1.00, and that's right here, okay? We didn't have to venture, it's not 1.01 or 1.02 or 1.03. We're staying close, making it very simple here. So the number that we pick up here is 0.1586. 0.1586, okay? In fact, it's 15866. All right. What does that tell us? The probability is 0.15866 that a motorcycle helmet would fall in a range up to and including 3.9, all right? Or the fact that we produce 15.866% of our helmets are made less than 3.9, okay? Now, that's all coming from our control theory, okay? This comes from the motorcycle helmet itself. We'll go back to another color here. It doesn't really matter. We'll use blue, all right? So that comes back to that this is what we're capable of. That's really important, is this is the process that we have. You know, what is it? In memes, they talk about the ones we have, the ones that we don't deserve or whatever, kind of. But this is the curve that we can produce to, all right? So once I'm going to redraw it, just clean it up a little bit, redraw it, basically the same thing, okay? Kind of, it's supposed to be the same thing. All right. Now we superimpose, we go back to our spec limits. Usually we talk about, in our capability, in our process capability, we talk about where are the plus or minus 1 standard deviations, plus and minus 2, and plus and minus 3. So plus and minus 1. Here's the +1, the +2. What am I saying? I'm saying this is -1 standard deviation from the mean. This is up 1 standard deviation. This is down 2. This is up 2. And in classic normal distribution, this is visually where they will occur. You won't get a thing, I'm repeating myself here, you won't get a thing where you get -3, -2, -1. They're not, that doesn't vary on the curve. The part of the curve that they occur on is very, very standardized, okay? So I could give you a blank curve like this and just say, all right, show the mean and then show me, rough out, tell me where do you think plus and minus 1, plus and minus 2, and plus and minus 3 are. And you could just go plus and minus 1, you're going to mark them off. They're like that. You know, -3 is not like way, way over here like that. I'm trying to say that this is a very standard thing. A lot of people don't teach that way, but that's a nature of these numbers, is your -1 is going to be here, -2, -3. Likewise, your 1, 2, and 3. And this is just a contrivance of the standard deviation. Okay, we're just using it to overlay to give us a visual and understanding about this data. Okay, all right. So I'm really dwelling, as you can tell, I think I've spent like 3 classes talking about this, but it's so ingrained with what's going on inside operations. And this could be either producing tangible things, or it could be it could be doing a service too. It could be like the time it takes to get the time it takes to get a process done, like a review, like if you're an attorney and you want to offer the fact that you will incorporate people, what's the average time it takes you to get somebody incorporated? And there could be a lot of variables in there, okay? And a business isn't going to be unaware. In fact, they're going to be wanting to know what all the variables are so that they have the semblance of control and understanding of what's going on in there, right? Okay, so service as well as tangible products, okay? In a hospital, talk about like in a hospital setting, there is no shortage. There's no shortage of places within a hospital that this is now being applied. Healthcare system, kind of interesting. I mean, there's different kinds of organizations and operations. Of course, you have hospitals. Within a hospital, right? There's many different things there. There's emergency. There's radiation treatment. There's what do you call it? Diagnostics. Taking blood samples and all kinds of things like that. A lot of that's now farmed out as third party, outsourced to specialty places. That doesn't all. What they try to do is do the most value add at a hospital, right? And why do we have such high costs in the United States? Because there is a conflict, okay? And each of you, for where you work, should try to find a conflict or think of it in terms of where's the conflict where I work with such a thing, okay? Because I want to move all the way from looking at the down in the trenches, this is what we look at, these normal distributions, to where does that apply? And they're applying it all over the place in healthcare. By general commentary, the United States' healthcare per capita is twice as high as the next closest country. And within a grouping of about 50 to 60 countries, we're put down at about the 40th position of quality. Okay, it's so complicated that every quote you see has nuances about it. You have to understand in healthcare in the United States, it's a great area to work because the next 25 years are going to be trying to bring the costs under control within the quality spectrum, and quality up is don't sacrifice any quality. In fact, you have to bring quality up while bringing the cost down. And the reason that it is that way in the United States, there's a number of things because we're not a socialist country and we're not apportioning healthcare out, that it's still very, very free market, that there's pockets of very expensive healthcare, whereas in rural areas will not survive if, for instance, Obamacare had gone through fully, completely, the hospitals at the fringe in the very rural areas were going to go under. So it's very complicated. And I suggest, it seems like everybody has let's say a great majority of population has a feeling one way or the other with a very simplified view of what it is. And the fact is it's been almost designed to be undecipherable. It's so complex with the supply chain in there and the way that physicians in the United States are allowed to just keep prescribing tests, unlimited amount of tests and things like that. And the core to this, okay, of what we're looking at right here with all these little curves that we have is one department after another has a series, they all stack up of all these processes with different variable outcomes on this. And in the United States, we're very conscious about death panels and things like that. And that's what the cry was going forward about. What Obamacare was about was going socialist, is that some people will wait forever and die waiting for a cure. And we don't have that right now in the United States. Ostensibly, okay? So healthcare is a great area. This is where they're bringing in all kinds of lean and agile and quality into hospitals. So I want to put it in context, especially in service industries, right? Colleges the same way. There's going to be a whole revamping of colleges, I think, to be more efficient. And that's a problem because a liberal arts college like Mount St. Mary's College is actually designed for latency and inefficiency, okay? Because a lot of deep thought happens about liberal arts types of things, general studies, that takes a while for the concepts to take place. It's not very sequential sometimes, and it's not very linear, okay? So anyway, I just want to paint out that this is getting used just about everywhere. And some industries have picked up on it, some of them haven't. And in the United States, the healthcare industry, there are many forces that would want it organized, streamlined, and there's many forces, probably equal forces, that are trying to keep it from becoming streamlined, to keep it free market, so that some hospitals can earn a higher margin. Okay, so just want to share why we're going into this. All right, I mean, what I like is that underneath all of our discussion, if you have a mathematical model like this, you can explain certain things in the economics of, let's say, healthcare and other things. Okay, so that was sort of a prelude to where this really gets used. Okay, so let me go back. I don't have the file from last week. I have to reconstruct a little bit of what we did from last week really quick here. But if we do a norm, okay, so if we use the norm, whoops, that's spelled right. I want you to know the, the formula in Excel that you use. This function, norm.s.dist, okay, so you see the normal dot distribution in there, in the name, okay? There used to be an older version of this. Hold on just a second. I'm going to put something in here so I don't lose it. So if I type in norm.dist, oh, I thought I was going to get a warning about that. A lot of formula in Excel get brought forward and improved, and quite often you'll get a little yellow triangle warning sign down here. It's not that you can't use the formula, but they've been deprecated. Basically, they've refined. Generally means that there's a much more refined version of a formula. But we're going to use something called the norm.s.dist. Okay, and if you can read my screen. Of course, it's not going to let me do it when I want to, okay? We're going to put in here, what's the probability? So norm.s.dist gives us the probability. It pulls the number out of the z table, basically, okay? So we're going to say, what's the probability of being down? We're one normal distribution down from the mean. And when I punch that number in, it comes out as 15866 if you round that up, and that's the number we pulled out of the table. So when you go to the table, when you go to the z table, what they've done is they've just run a formula. Basically, this is an Excel sheet. Normally, when I run the 8-week version of this course, I actually have everybody produce this table because that activity, you start getting a better feel for what the numbers are all about. Okay, go back here. Okay. So if you remember, I just typed the number in there, 0.15866. I took it out of the table. And then when we calculated it, this is the formula you want to remember. I mean, you're going to use this in operations all the time. Sometimes it's buried underneath a higher level dashboard or whatever. But that's the number you're going to use. And what does that tell us? It tells us when we come back to our drawing that there's 15.8. I'm not going to draw all the digits because it's a little bit difficult for me to break these things out. 15.8. Okay, so 15.8% of the curve Oops, I'm doing it in the wrong place. Let me see if I can grab that. Okay, that says 15.8% of the curve occurs up to and including -1 standard deviation. I'm actually maybe distracting everybody by using such round numbers because the number that we might be interested in might be 0.92675 or something like that. So we're using big, fat, easy numbers like -1 and whatever, but you have to be ready for, in real life, we're going to be using numbers like 0.923. You know, they're not convenient numbers. They're not easy to remember, but there's a reason why I'm using the whole numbers of standard deviations here, okay? So it says 15.8% of the curve lies underneath the curve to the left of the point of interest. When we use symmetry, what we can say is the area of the curve above 1 standard deviation, which is symmetric on the other side of the mean, would also be 15.8, okay? Okay, all right. So what we're playing out here in this class tonight is that when we come back over here, if I take 2 times that is equal to that times 2, Okay, that's 31.73, et cetera, et cetera, et cetera. Okay, and if we subtract that from 1, we get 68 point blah, 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 68.3, let's call it. So what we did is we took 1 and we subtracted this area here, we subtracted this area here, which leaves us the area in between here. Use a big fat blue pen here, okay? Okay, so that area in there is 68%. We went around the numbers here, real rough. And what we developed is the concept of what they call the empirical model of the normal distribution. We talk about whole numbers of distances between plus and minus 1 standard deviation, plus and minus 2, okay, and then plus and minus 3, okay. And when we do this, we talked about it in class one night. Ludwig had it nailed. He remembered this from earlier courses. Let's see, this one here, okay. So we have 68% between plus and minus 1, okay. Let's go calculate. Let's use Excel to calculate this. All right. So instead, we're going to come over here. I'm going to grab this cell. I'm just going to drag it over here. Norm.s.dist of, let's say, -2. Okay. So now we're going out further on the curve. We're going out to, here's the 2 over here. That's -2. Okay. -2. And the area to the left of -2 is only 2.275%. Okay. So I'm going to drag this formula over, and we're going to multiply by 2. And I'm going to drag this formula over, and we're going to say 1 minus that is equal to what? 95.45%. So let me drop these down. Okay. So the area between plus and minus 2 is 95.45. 95. All right. So we generally, when we're just slinging the terms around, we say 68, 95. Understand that there's some decimal places there to be very exact. Okay. And then finally, out at the plus and minus 3, how much area is between these two here? We'll take all 3 of these, copy them over because I know I'm going to use them. And I'm going to change my norm.s to -3. Okay. And that drops everything through. Okay. So only 0.135% of the curve, or 0.135 of our production, is going to take place less than -3. Okay. That was way down here. This is little, actually I drew a lot bigger than I should have. Okay. All right. The little tail here, even though it starts becoming hard to detect visually, it remains important. And it says the area of the curve that's built, like if we're building these motorcycle helmets, it's saying that 0.27% of them, 0.27, like 0.25% of our helmets are going to come out less than that 3 standard deviations away. Okay, and if we run the same math as we did before, so let me mark this in here as -1. This is how many standard deviations we are. Standard. This is how many standard deviations we are from the mean. -2, -3. I'm just going to paint that so we know what's going on there. Okay. Okay, and these are the important numbers down here. These are the percentages. Let's turn them into percentages. We'll go to home, we go to number, and we're going to put it in there as percentage. And we'll let two decimal places in there, okay? What we just went through is a core simplified, simplest version. It's not simplified, but it's a simplest version of understanding process control. So if you get into a company that's using this and you go to a weekly meeting about this, most of their processes will probably be based on a 3 sigma system, which is plus or minus 3 sigma, okay? Any individual process was probably 3 sigma, but overall we're going to strive for 6 sigma, okay? Because now I'm about to blow our minds here a little bit. Okay, so let's grab, we keep hearing all about Six Sigma. Let's show what Six Sigma is about. I think I did this in class once, but let's change this to -6. So now we're talking about a tiny, tiny, tiny left part of the tail, okay? I have to change my equation to say, what's the percentage, norm.s.dis, to the left of -6 sigma, right? Okay. Notice some wacky numbers that are coming up. We have something to the times 10 to the -9th. So we know that this is really, really small, okay? In fact, what I need to do, or what we need to do, is grab those cells, and we're going to say that it's a number. I don't want to use scientific notation. I just want to use decimal notation, and I have to take it out to something on the order of 15 places. Let's just put it out to 15 places, okay? Might not have needed that many. I need to go out a lot of places, okay? I'm going to blow this up so we can see it better. Okay. Okay. And the reason I reformatted the numbers is that you can see them better. If you count carefully, there's 3 zeros, 3 more zeros, and then 2 zeros and a 1. If you're playing closely at home and you understand what we're looking at, is that's almost nothing. Okay, that's a very, very small number. I want to reformat that number there. Hang on just a second. That's the one I was after. I must have missed it when I grabbed them. Okay, the reason why I wanted to show you this is one tail. Okay, so the whole idea when we're talking about normal distributions, you'll hear in other kind of tests, there's like the two-tail t-test and the one-tail t-test. It has to do with these are the tails, way, way to the right and way, way to the left. Okay, we're way over here at -6. Okay, and you're wondering, wow, what process in the world is going to need that kind of precision? Okay, and we can see that one tail is 0.9 billion or billionth or 1 billionth. Everybody following me on this? Can I hear an amen? Okay. The why I dragged us all the way through what I did already is that whenever you see the word Six Sigma in industry, like all over the place, all right, what I'm showing you here tonight is a major takeaway to remember, okay? The reason I'm showing you this is when there's a number that gets associated with Six Sigma, which is our yield number or a failure number, that at first doesn't completely make sense, okay? And there's this number that hangs out there for Six Sigma. It's something on the order of like 3.4 parts per million, okay? Here we're talking about if we round this number, we're talking about 1 part per billion, okay? We rounded it up to 1 part, it's really 0.98 something parts per billion. Count your zeros. There's a set of 3, there's a set of 3, there's a third set of 3, and that comes out to billions. We're now down at the billions. So you have to think about, in a hospital, what function can we even do 1 billion times to have an error like this? All right, okay. So there's 2 things I want to talk about as far as quality and Six Sigma goes about that. Right? You'll notice that we multiplied the one tail by times 2 to get the area for both tails, and it comes out to, if you do your math, if you look at these numbers carefully, it's if you do rounding on here, it's 2 parts per billion. All right. So our total failure in Six Sigma is 2 parts per billion, and you're going to come up with a perpetual question of, I'm baffled. I took a course in operations, and when we did the hard math, we found out that it was 2 parts per billion is the failure rate if we're looking at a Six Sigma system. So the number of sigmas is really plus or minus that number. It's -6 to Six Sigma. What we're saying there in Six Sigma is we want a yield, or we want a failure rate so low that it's outside of -6 and it's outside of +6. All right. So I did mention at the beginning of this that I was going to blow your mind with such small numbers in the industry. Where do we get those from? So the first thing is you're going to go into a meeting and everybody's going to be shooting around the term 3.4 part per billion, or part per million rather, right? So one of the major points of my going through this to such extreme detail is this. What's the difference between 2 parts per billion and 3.4 parts per million? Okay. Here's the thing. Now we're going to bring it back to reality. And when we look at how a process works, okay, there can be some systemic or systematic things that are going on in our process that on any good day, the shape of the curve remains the same, but what ends up happening is, I'm going to redraw it down here once again. Redraw this once again like this, okay? So I'm redrawing what we had up here. Okay. On a good day, our process is centered. There's a huge point of why there's a difference between 2 parts per billion and 3.4 parts per million. Okay. It has to do with the fact that we know that while the shape of the curve, the variability doesn't change, the center point of the process might. It's more likely the center point, we're going to get something called drift. Okay. And in any process, it could be anything. You get a drift. Let's go service process. Why would, let's say that, nowadays that they do knee and hip replacements all over the place. They've got this thing down and they use these kinds of concepts to say, how can we get all of the hip replacements we can in one day done, in a normal day? So if you talk about processing them through, they'll be doing the hip replacement, and then there's a changeover where they have to clean up the operating room and get the next patient in there. So let's say they could get 3 a day. Each of them takes 2 hours, and everybody has to be there early. And within 8 hours, you can get 3 2-hour operations done. That's how this applies. Okay. But what happens if you all of a sudden on one day the nursing staff you got is the younger set, less experienced? And instead of 2 hours, it starts taking 2.5 hours, right? That's where you're going to get an average that drifts, even though your variability is not going to change. You're going to get a change in the average hours it takes to do a hip replacement, okay? And that's where Six Sigma, these two numbers, okay? The difference between going through professional training for Six Sigma and going for an MBA is what I'm giving you right here, okay? So I always call these things the edge. When you go through Six Sigma training, all you're going to hear about is this. You're never going to hear about what the reality is, and it's going to bother you because you want to use your Excel, right? And you're going to come up with those funny numbers, 1 versus 2 versus 3.4 million. And here's the issue here. Six Sigma says we're not perfect. Every day that there's some variability in the average. And what we do is we allow the average to move by 1.5 standard deviations plus or minus, all right? Okay, so what does that do? We're going to bring it on home now. This is like the core of the process control, okay? Six Sigma is right at the core of it. What happens is, I'm going to draw it underneath here. Let's try that straighter, okay? Not that that was much better. There's our mean. And what we're going to do is, before we had gates, our process control was right here, right? So our lower control limit, the LCL, the lower control limit, shouldn't be hard to understand that, lower control limit, and our upper control limit says we know by practice and design that we can get -6 to 6 like this. All right, we can get our process to fit through these between two goalposts like this. We're in real luck if the rest of the world agrees. In other words, the lower spec limit, everybody keeping the difference between these alive? The spec limit comes from customers or compliance sources. The lower spec limit. There's all kinds of health associations like JACO and HIPAA and all these other places other standards that we have to uphold, okay? And a combination of all them say, with all that said, what is the upper and lower spec limit? What do we have to meet and what can we meet? Capiche? Okay, that's the difference. This thing here is what we can meet, what our process does, and this is what we have to meet. That's what we have to meet. And if they're perfectly aligned like this, that means we're literally 100% capable, but God forbid if our process starts drifting. Why is that? Okay, so let's say these are our spec limits, okay? Now what happens is if we've drifted down, it looks like this, okay? We've moved down, so we're picking up a bigger loss down here, okay? We could do this with pictures. Okay, we had some math, we can use the math and apply it, but we're using pictures here where this thing might have drifted down to sigma. Okay, so we talk in terms of sigma. And all sigma is, remember, is a yardstick. It's the average distance to the mean of all the points. It has a tangible, useful number. Okay? Okay. Hang in there, everybody. We're almost to the end here. Okay? I know I've been doing all the talking, but I guess that's the nature of doing this by doing this remote. Everybody get their head off the desk, okay? Pay attention. Take your shot of espresso here, and we'll finish this off, all right? Okay, so what happens is, what we said before, if we had a 6 sigma system, and this moved down by -2 sigma, moved to the left, okay? That means that the spec limit is now matched up with what? Okay, so now it's lined up with our -4 sigma. What used to be -4 sigma when we move to the left is now aligned because we moved down by 2, okay? So our rate of loss or scrap, I hate to put it that way in terms of, in medical world of, patients that have some fault with their operation or whatever, okay? What ends up happening is we've moved to the left without reshaping the curve. It pretty much stayed the same, but the average drifted way down. Everything drifted together down. And so now what is our rate? Okay, so if we go back to Excel, okay, when we first measured everything to the left of -6 sigma, it was 1 part per billion. Remember, we're rounding this number here, okay? So let's see, we didn't use -4 yet. Let me grab these numbers. We need another column, okay? So for this problem that we're looking at, okay, what is the loss? What's to the left of -4 sigma, okay? We've got to change our number in here to -4. Okay, let's just look at the first line to begin with. So we have one set of 3s. So now it is 31 parts per million, right? You have to look at the zeros. I'm putting my cursor right where there's 3 zeros to the left, and then it goes, 31. So that's 31 parts per million, okay? So we could see the loss went from 1 part per million to 31 parts per million. We're losing a lot more, whatever it is that we're losing. Okay, so to just give you an idea what happens when you drift, some point, it used to be here, some point here drifts, when it's done drifting, we're losing all of the stuff that used to be in the good range. That's the problem with drift. Drift will get you. But at least our standard deviation, the average distance to the mean, is not changing, okay? So that's how we model these processes. Now in real life, you might get some variability in the variability. In other words, the variability of the standard deviation and such. But for any of the things that we're studying, we assume that that shape never changes, it just drifts down. Okay, now what did I say up above? We allow in 6 sigma, by definition, we allow 1.5 standard deviation drift in either direction, okay? Go back up here again. Pick another color. Okay. Okay, so I'm going to try to use the lines from above. I'm going to drop, these are the spec limits. Remember, this is what we had to stay in the middle of. And for a while, we had our process completely aligned. We had 100%, capability, where our process we worked on for 10 years was able to fit precisely between the upper and lower spec limits, but we hadn't accounted for drift, and the drift has taken us away. Okay, so instead of -2, okay, we've drifted like this. We've really drifted -1.5. Okay. Now, you might have caught something when we went over here. What we caught was, now when we're talking about this drift, we only talked about the left-hand side loss, okay? So our curve shimmied to the left, and we went from 1 part per billion to 1 part per billion to 31 parts or 32 parts per million, like a lot, 31,000 times as big, right? That's how many more we lost per million, okay? Okay. But usually we do symmetry. Okay, usually, what happened to over here? Why didn't we add another thing over here? Well, you notice that the point that used to be -4 sigma when everything was aligned well, the thing that was -4 sigma here, it drifted down, so now it's aligned with the lower spec limit that the customer wants or the world makes us comply with. But what's now aligned? What's the loss up here? Okay. Instead of, if you remember, it was 6 sigma, what point of the curve now aligns? Now that we move to the left 2 sigma, this is now the 8 sigma mark, okay? All right. It's so small compared to the left-hand side that we don't even bother to add it in. It's implied, but not added in, okay? So we sort of break the mold a little bit there, but we're talking about a number that's in parts per trillion or something like that. The height of this curve is so small at 8 sigma. You're so far out from the mean now that you need a microscope underneath a microscope to even find it. Okay, that's how small it is, right? Okay, so I gave you an example here, and now we're going to look at, I wanted to use other numbers so you get to see the numbers that are different. Here we said it shifted down by -2. Okay, so now we're going to say that our 6 sigma system, where we allow it to go -1.5 to +1.5 sigma drift, okay, because so the original mean, let me use blue here because the original was in blue, the original mean was here, that was our center point, okay, so we can, and I'll try to do this in dotted, I'll draw dotted, so we can go up as far as 1.5. I'm only showing one side, but it could go either direction. As long as our center point gate is between -5, 1.5, and 1.5, we're fine, okay? So now that this thing shifted down by 1.5, what part of the original curve lines up with the spec limit? That part of the curve is 6 minus 1.5 or -4.5 sig, okay? All right. Again, this is why you're getting an MBA. You may end up taking 6 sigma sometime, but they will not get into the underlying rationale for this, and it might drive you crazy because you want to know where everything was derived from. So we can bring it home. We're going to know what is the scrap at -4.5 sigma. Okay, so we're going to add one more column here. Drag this over. We'll change this to 4.5, -4.5. And make that -4.5, okay? All right, so here's the quiz of the night. What does 3.39 look a lot like that I've been talking about? Okay, so that's 3.4 if you round it, parts per million. There's 3 zeros to the left of the cursor, and then it goes 0, 0, 3.4. So it's 3.4 parts per million rather. Okay. And that's the story of life. Okay, and this is the point that I like to, mathematically speaking, pretty much the highlight. As I say, it's the difference between getting an MBA and getting a certificate. You could get different belts, like in karate. You can get different belts in 6 Sigma training, and there are master black belts. I think there's master black belts. They've had people that are the gurus of that are so high that they have like new names for the black belts for really high version of that. Okay, So I've like been talking a long time, like what? Maybe not that long, only an hour, right? So there we have it. That's where when you're out on the street, you'll hear Six Sigma. This is core to the training. It's almost like you have to get a tattoo of this on your forearm if you're a Six Sigma person. This is what you're allowed in Six Sigma. The whole world worked on it. So you might remember there's a part B to this, a little bit of a part B, and it said, well, where in industry do we ever do anything a million times, much less a billion times, to be able to measure that small, all right? The reason for that is if you have a sequence of operations, each of them is probabilistic or stochastic, all right? So you're going to have some average, but it's normally distributed. So this is A, B, how many stages do you have? I, S, Z, how many stages do you have? Every time you have one of these operations, the probability from here, whoops, my pen didn't work right there, the probability from there times the probability from here times the probability times the probability times the probability, you can end up with something very, very quickly within 5 operations where you're now looking at Six Sigma levels. That's where Six Sigma applies to everywhere else in the world. In semiconductors, which Motorola was doing, okay, what they do is they pull a silicon crystal that looks like this out of a bath of molten silicon, okay? This could be 5 feet, 8 feet, 10 feet long, and they slice it, and they get a silicon wafer like this, and then they etch it and zap it, chemically treat it, and do nasty things to it and everything, and it ends up as being a circuit, some kind of electrical circuit, and then they take the round thing like this, that's round, believe it or not, and they chop it. They literally bandsaw the thing with a special micro bandsaw here. And each one of these is the same thing. Each one of these squares is the same thing. You lose all the ones around the edges because they're not square. But what they do is they just remask, they've just done the same mask on every one of these squares. And once you remove the known bad ones, which are the partial ones around the edges, let's say, a 5-inch wafer is a standard. Maybe you ended up with 128 chips off that, 128 circuits. They get chopped up into these little guys like this, all right? And then what they do is they solder them into ceramic things that look like this, and these are like now human size. You can actually see this, and they have wires coming off there, and they put them into circuit boards, and that's what an integrated circuit is. It starts out like this as a crystal. They slice it. So I slice this. This is like flat. This is like a micron thick, And then they etch it and make it electrical. They do all these electrical layering up on it and all kinds of things. And there's many of these on a round wafer. They chop it up, and these end up in a stack, and they start testing them. And within any one of these, like on one wafer, they got 100. Let's say they pulled 128 chips. They normally would get 128 chips out of there. Every one of these chips might have like 10 million transistors in there, okay? And that's why those numbers are very applicable to semiconductors, because you get millions and millions and millions of little transistors, and they all have to work, okay? The rest of the world benefits because they've drawn parallels to it and such, okay? And that's Six Sigma really started with Motorola, okay? So we brought all that home. Motorola. I'm not going to spend a little time. I can't write that way. Someone say something or write something. Question, tell me. I have to turn a light on, by the way. You can see my room got dark. How many people are like totally amazed by that? Like this was the highlight of the course. I should be hearing like all amens right now. Anybody awake? Someone let me know that you're awake. Maybe I'm just talking to myself. Okay. I'll talk about the paper after we get done with this. Okay. All right. But good to see you, Cynthia. I hope orientation went well. Okay, everybody's still there? All right. Now, this was being recorded, so I've recorded this probably 10 different ways already, but I'll post this on YouTube so you can get back to it. All right. And what I am going to do now is gentleman that produced some very, very good videos. There's two different gentlemen on YouTube that I use their videos. Okay. So if you go to E-Class, I think for tonight, I think it's E-Class for tonight. Yeah, class 606, 12th of August. If you go to tonight's class, I've put 2 different Excel videos in there that you're going to want to watch that show you the norm.s.dist, shows you norm.s.dist, it shows you how to use that function. Okay, stand by for just a second. I'm going to throw a light on in my room. It got dark where I am. Hang on just a second. Oh, the light goes on. All right, that might be better. Okay. Anybody else have any questions? Any fascinating insights? Where to apply this? Okay. All right. Might have been. Yeah, I see a yay. It might not have been an amen, but I got a yay. All right. So far, so good. Yeah. That takes a lot of stepping through what I just did. The way that you pick up on it is not like one time through. Statistics at all takes a little bit to understand, but think of all the statistics you ever had with standard deviation and the Z table and whatever. Let's see. Trying to get my screen to refresh here. All right. So I went all the way through this. It does look pretty dense, so it's almost you have to go through the video to understand what we've got, how we got there. But I find it very interesting. I've gone out sometime in industry, if you happen to be networking or having a lunch with somebody that's been trained in Six Sigma, just ask them casually, what do you think about that 3.4 part per million? And if you dig a little bit, and I have with people that are trained in Six Sigma, that they don't understand the underlying statistics, which I think is very liberating when you understand where this comes from and you're able to use such things. I'm going to blow this up. Such things as the norm.s.dist function. Now there's another inverse function, okay? The other video that I have posted in here is, I just want to make sure I have them labeled correctly here. So here's a YouTube. Okay. So the inverse function, if you remember when you've used this before, I'm going to go dig out that, right? Sometimes you want to know a point associated with a probability, right? So we came into, tell you what I'm going to do. I'm going to take a shot of this, okay? So we came into this table, generally the way you learn this and the way that you pick up on this is the way that the direction that we came in, okay? We looked at a curve, we looked at some curve, normal distribution curve, right? There's a little bit of delay on the update in this file, so hang on just a second. Hopefully there's not much of a delay from me to you where you're watching. But for some reason, it's not going down for me. Something holds it up from showing what's going on. Okay, so normally, no pun intended there, normally, grab the drawing thing here, right? Normally, what we did is we looked at a normal distribution like this, and we said, what's the probability at some point x of I? I put x of I because it's like point of interest. I is for interest, okay? Some value, and how far away is it from the mean, okay? So we just live by this. I'm just repeating this many times because this is what it is. You have to repeat it, you understand it, that this is core, pushing the numbers around helps you understand this. So a lot of times we want to know what's the probability associated with some point, but sometimes we want to know what point do I need to assure a probability, all right? So if we say we need a failure rate, our acceptable failure rate is, I'm going to pick an odd number here, is 20%, and we have a symmetric setup, just like we've been talking about here. So that means what point here, what x of I is associated, and this is x of I, and it's less than the mean, all right? And here's x positive of I, okay? So this is symmetric around the mean, okay? So we want to know what's the yield, or I'm sorry, what's this point? How many standard deviations are we, much less pounds? How many standard deviations do we need to be away from the mean to assure 20% yield? Or I'm sorry, 20% scrap rate, okay? So we need the inverse function here, all right? So when you go back over to the table that I'm now stuck in here, can't move it, all right. Now what am I gonna do? I'm stuck, my window won't move. Oh, there we go. All right, so here we go. This is the Z table just for the negative side, okay? So what we would do is we'd look into this table and we'd look for 10%, okay? Because remember, this table only shows one side, like one tail, okay? So there'd be 10% here, as there would be 10% over here. And that says we need an 80% yield or an 80% yield or 20% failure rate. One tail is going to be 10%. And we look in this table, here's all the probabilities. We'd have to look in this table for 0.10, and there it is. You have to do a little extrapolation, interpolation, or whatever, right? Where's point? So here's point, the closest we have is about here, right? So this says that we need to pick a point that's minus 1.28. Okay, so minus 1.28. Let's go back over to our, well, we're in Excel. I forgot I copied it over here. All right. 1.28. So let's just check that out. Minus 1.28. Grab these numbers. Drag them to the right. Do this. Okay. Oh, we have to do something different. I'm sorry. We're doing the inverse here. Okay, that was the point. Okay, so this is in sigma here, and that relates to 10%. But what is the actual number of pounds here? Okay, we got it in. Right now we have it in standard deviations, but this is a different kind of problem. Let me color it with orange. Okay, so now we want to know what is the number of pounds associated with minus 1.28 standard deviations. So we have to go back to our Z. Our Z is going to be equal to, if I can page down, it's not paging down for me, stand by. Got a little slow down in the cockpit here. Right? It's supposed to go down. Okay, if we remember what Z was, Z is equal to point of interest minus the mean over sigma. Okay, and so we're going to back out. What we're looking for is we have a Z of minus 1.28, and we're going to need to solve for X. So it's going to be 1.28 plus the mean, which was 4 pounds, remember? So we're plus the mean over sigma. Not sure if we ever picked a sigma for that or not. Okay, so you use your sigma in there, and that will give you your point of, the point that's associated with 20%. Actually with 10%. Okay, and it's going to be some distance from the mean. There's your mean. It's going to be right here, and you're going to know here's this X, and this is down 1.28 standard deviations, and you look for the point above 1.28 standard deviations. Those are the 2 points that you're going to come up with. So that turns it back into the physical number that you're actually shooting for, all right? Okay. Now, I'm going to go back over to E-class, because what we're working on here, everything I've talked about here, including the rest of the videos in E-class, have to do with statistical process control. I've given you the forward norm.s.dist function. I've given you the inverse function, how to get the point associated with a certain percentage that you're interested in. So we backed out of the table the other way. We started with a percentage, and we came back to what is the number of pounds associated with that percentage that's acceptable. Okay. Now I'm going to start. I'm going to start us on this video. This is a really important video. It covers 2 or 3 major points. You're going to want to follow this video very carefully for the final. I put questions together that involve everything I just discussed tonight, at least last week, and several maybe other classes where I brought up how these percentages and how standard deviation works and such. But this video is very good. It takes a very common example or something that we know about in real life, a coffee maker, and how hot should the coffee be, right? Now, after that, the topics that we cover have to do with C charts, P charts. This is a P chart, a C chart, and while you're listening here, you want to jot something down, okay? I think it comes out in the videos. But you have to think about why they called it a P. What does P stand for here? What does C stand for? And then finally, we have X bar R charts, okay? All right? And so remember, this is being recorded. You can go back to this. You want to jot this down, that the P chart, though, has to do, now we're going to move a few steps forward. What I'm discussing now is when you actually have some production facility, and you want to express defects, okay? So defects are a huge term when you consider statistical process control. Defects are everything that happened outside what the customer wants, okay? I'll go up to one of the better drawings here. Come up to, boy, there is no better one, okay? Just to remind you, I'm going to do it really quickly here, and I'll draw it. Draw it with blue or something. I think that's black. Okay, so remember, the lines that we show on here are the average. We show our control limits. We show control, like what our actual process is. Excuse me. And then the customer sets spec limits. And does our process fit the spec limits? That's the whole idea. These black lines are the control limits. The red ones are the spec limits the customer has. And let's say that we need to get these outboard black lines to align, to at least align with what the customer wants. In other words, we have to squeeze our process. What does that mean? We have to get more things good. We have to bring in the tails inside what the customer wants. So this curve is now going to go like this. This is the effect we're after, okay? It means very few things are getting missed outside what the customer wants out here, okay? So you have to think of it mathematically and visually and then pragmatically what's happening out there, you know? A t-shirt, you might do a color check on a t-shirt. You know, these days, color is amazing, you know, the impact in sales, on marketing, on luxury goods or whatever. It has to be a particular color of yellow. Anybody that's worked around color items, especially like in print and things like that, there's a standard called Pantone colors, all right? And that means when you pick a logo, it's not just the shape and everything, it's like what blue, what Pantone color are you going to use all the time? And if you don't tell people that they'll use any blue whatsoever, you're going to have all these logos on all your things, different colors of blue. So to give you an example, you know, Pantone, the way that they do this is they have a digital reader and they can shoot something with a little gun and it will tell them what color blue. It'll align it with what Pantone it is. And you want to, you know, that's a quality check. When you have graphics materials made, like brochures and whatever, you'll have a quality department bring in what the marketing group did, and shoot it and make sure that it's color. Anybody that's ever done any licensing, it's very controlled that way. If you get into a licensing agreement with Disney or somebody, you have to like show that all your work is to their color, even down to their colors, much less all the other specs involved with it. Just to paint a sharper picture of what this curve means here. This curve, this means that Disney, you're allowed to continue marketing Mickey Mouse, whatever, t-shirts, because you're using the correct colors for Mickey Mouse, whatever they might be. Okay, so this has real world, immediate real world use, and maybe where you work. One of the comments I want to make, because this is the last evening to be able to talk about this at all, is that a lot of these processes you're going, I never even hear about this where I work. Well, there's different levels to which you can bring this into where you work and get highly rewarded. Okay, one of them is just awareness. Most operations have no clue that this exists in their early stages. And gradually, as they start having more failures with customers, they have to look at the processes, they have to see what it causes things to be narrowly or widely dispersed, what's causing variability in your system and whatnot. And so the opportunity for this course is to look at what things go wrong where you are, okay? That's one of the first things, not the only thing, but look at what goes wrong. You can also look at what goes right. But look at what goes wrong, and can you start, even from a vague and then progressively more refined, can you look at a process and say, this is what's causing variability. If we remove this, we can become much better like this. When that happens and people aren't doing any analysis, these curves are taking place under the covers, so to speak. They may not be aware of it, but this is what they're doing. When you say, I need to get better because the customer is unhappy, is you're making more things happen within their spec, and there it is. Okay, so I just want to bring home, I don't do anything that isn't practical and valuable, by the way. So that's why I ended up, I think, teaching these courses. And so you can have a visual and a mathematical background about how this actually works. All right. Okay, just kind of bring home the course here in the last few minutes. All right, so we have a video. I want to get it started so you have a chance to think about it a little bit. I'm going to start this one. You can rerun it, etc. They're all available here. The P chart is for a proportion. This means that when you're watching a process, you want to make sure that the defects don't go above 13% or 6%. It's a proportion, okay? So it's like a ratio of bad to good, right? You want to keep your P chart, okay? And if you can see from my screen here, in process control, what you'll have is you'll have these digital readings like dashboards, and you'll have this line down the middle is your average, and these marks above and below are your control limits, okay? So you know where you need to keep the process, and you can see some of these points in here from the video. And what happens when a point goes outside your control limit? Do you panic, just run around with your hair on fire, or is it a statistical probability? Is that we did say that there is some probability that we're going to fall outside the spec limit, okay, or the control limit, either way, right? In a count, in a C chart, it's a raw count. Rather than proportion, you're saying that if you have a 2x4, an 8-foot 2x4, how many knots, visible knots, are you allowing, okay? There's different grades involved with it. So if you're grade A, there might only be 1 knot per 8 feet. And for whatever reason, it might be for pallets or something, there might be a really low grade 2x4 made out of pine, and you might have, you might allow, 2 knots per foot, which would be, 16 knots per 8 foot or something like that, That's what count is. That's all the differences between a P and a C, and some processes you want to set up so you count the things that go bad, and some things you count them, but you turn them into a proportion. Okay, and then the last type of measurements you're going to see in production is an X bar chart. What is an X bar? X bar is a mean, all right? So what you're doing as you're running batches, you're looking at the mean. Is the mean, what we're looking at here in this table, if you can see it on my screen, as you look here, we're looking at from batch to batch, is the mean changing? And for some reason, this batch had a very low mean. I don't know if that is good or bad, but it's outside the control limit, which is marked up here, okay? So you're going to look at how the average in the batches is changing. It should hang really tight. Really ideally, you don't want no variability in that. It wants to be very tight. And finally, we talk about an R chart. And an R is the range, okay? So very briefly, what we talked about was, once again, there's a standard deviation. And we talked about, I'm sorry, a normal distribution. And then we've talked about, we used a concept called normal distribution, which is the average distance to the mean of all the points. But there's another cheap way of looking at variability, okay? So the reason that we use standard deviation, it's a measure about how dispersed or concentrated our points are. So this is very dispersed, and this is very concentrated, the rate around the mean, okay? And so the average distance to the mean is going to be very low for this and very high for this. The average distance is going to grow, all right? Well, what's the poor man, if you will? What's the poor man's way of checking variability? How about the range? Look at your low point, look at your high point in a batch. That's what the range is. You're going to look at, and the range will be the distance. What's the distance between your high, is your high point measured, and your low point measured? And the range is just going to be the distance. It's an R. Okay, that's not an A. Try to draw a better R. There, okay? So your range is the distance between these points. If the range goes up, your variability went up. It's sort of a simplified poor man's version or whatever, efficient man, lazy person's version of a standard deviation. It's expressing the variation. But what I'm going to do is run at least a couple minutes of this while we have everybody on the line. We still have 5 people on the line, which is fantastic. Okay. I guess we did pick up Ludwig and Helen. All right. Here we go. So I'm gonna run this for not too long. It's 8 o'clock. I was shooting for 8, and if we run a few minutes here, do think about any questions you have about the final will be on Six Sigma. It will be on these types of C charts and P charts, etc. That should be able to be use the videos to be able to answer the questions and any homeworks that we might have had or chapter work that you can find that we've had in the course. All right, so I'm going to run this, and you're going to see an application. Why I'm running it right now is I still have everybody's attention, and this will give you an idea of like making coffee systems and controlling the temperature. You know, nowadays you can buy a coffee maker for $10. It's mind blowing. You can get the coffee pot out of glass with a metal band, a formed plastic handle on it at the top, and get this heater that whoever produces these produces them on everybody's name. Okay, so there's only like probably one producer of coffee makers in the world these days because they're so cheap. They're like $10. You know, that's delivered. You know, that's not delivered through Amazon, but you know, if you go to a big box store somewhere, you can buy one of these for $10, right? Think about this. You know, that could end up damaging somebody. You could actually heat the stuff so hot that it burns somebody and such. You know, the liability behind your process is there. Your attorneys want to say, your company's attorneys, if you're a coffee maker, are saying, tell me you're not going to run into a lot of lawsuits. Tell me that a way, or tell me how you're controlling the temperature of coffee that comes out of this. And the big example goes back to the McDonald's case where somebody had a foam cup of coffee between their legs while they're driving, and when they squeezed it, the top popped off it, coffee went all over the lap, they get burned, and they sue. If you go to the lawsuit about what that was about, it wasn't just a simple fact that somebody got burned. It was that that McDonald's, when they subpoenaed all the information, had charts that showed the higher the temperature, the lower sensitivity a person's tongue has to the actual quality of the coffee. So we can start increasing the temperature of the coffee and reducing the amount of coffee in there until a point where people are starting to get hurt by it. And what's the cost benefit? If we keep raising the temperature of the coffee, when does it get offset by lawsuits? That's what McDonald's got nailed on, is that they were actually factoring in human suffering into their cost benefit equation. And they said, we can afford all these lawsuits. All these people are going to get hurt by getting burned by the coffee. Okay, so some of you might have known that case, some of you might not have, but that is why McDonald's got sued on that, is that they had inhumanely factored in human suffering into their cost benefit of heating coffee up so hot that you can't even taste it anymore. All right. So anyway, that was a 3-second version of it. Okay. So I'm going to run this YouTube for a little, just so you can get a gist of what's going on in there. But there's several very important concepts that are involved that go along with what I described tonight about moving the goalposts so that you're fitting what the customer wants. Okay, so I'm going to run this, and then we'll stop for comments in about 5 or 7 minutes. Denoted by. Okay, let me try that again. I had just muted my mic when I started.
Now I hear you.
Yeah, let me start this over again. Okay. What I meant to be telling everybody is make sure you can hear this when I run it. I'm going to run it for about 5 minutes or so you get a gist of what it. Stop. So that you can see in the making of coffee makers, the liability involved with it. All right, so I'm going to run this now. If you can or can't hear me, just shoot me a little chat note down there. I'm going to be watching down there. I'm going to turn off my mic though. Okay, one more time here. I'm just going to try to get my mic close to my own speakers on my. I'm not sure how to get system sound to play out over what you're listening to. So I'm putting my mic right near my speakers. We have looked at process capability in terms of 3 sigma, 4 sigma, 5 sigma, and 6 sigma levels. Another important way to express process capability is in terms of a measure known as the process capability ratio, denoted by C subscript P. Cp can be calculated using the formula shown. Think about this calculation as a question. We are looking at the range of the customer's tolerance, that is, upper specification minus lower specification. The question we are asking is, within this range, can we fit 6 standard deviations? If we can do that, then our answer will be greater than or equal to 1, and we say the process is capable. If we cannot do that, our answer will be less than 1, and we say the process is not capable. How does this CP measurement line up with the scale we saw earlier in terms of 3 sigma, 4 sigma, 5 sigma, and 6 sigma levels? To answer that question, let us look at our 3 sigma capable coffee machine, Model A. This machine is able to produce coffee at an average temperature of 160 degrees, with a standard deviation of 3.33 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit 3 standard deviations on either side of the bean. Calculating the CP, we get 170 minus 150 divided by 6 times 3.33, which comes to 1.0. Imagine we have a custom design ruler that we are using to measure our process variability. Instead of being marked in inches or centimeters, this ruler is marked in standard deviations. The ruler itself is 6 standard deviations long, so say we call it our 6 standard deviation ruler. Looking at the CP calculation as a question, can we fit 6 standard deviations within the range of our customer's tolerance? The answer is yes. Our 3 sigma process is capable of giving us what we want, but it is at the bottom of our process capability scale. Let us now look at our 4 sigma capable coffee machine, Model B. This machine is able to produce coffee at an average temperature of 160 degrees, with a standard deviation of 2.5 degrees.
Within our desired range of 160 plus or minus 10 degrees, we are able to fit 4 standard deviations on either side of the mean. Calculating the CP, we get 170 minus 150 divided by 6 times 2.5, which comes to 1.33. For this process, our 6 standard deviation ruler is a little shorter than for the previous one, because the standard deviation here is a little smaller. Looking at the CP calculation as a question, can we fit the 6 standard deviation ruler within the range of the customer's tolerance? The answer is yes. In this case, we can fit the ruler not just once, but also a third more. That is what the CP value of 1.33 implies. We have moved up a notch on our process capability scale. Let us now look at our 5 sigma capable coffee machine, Model C. This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 2 degrees. Within our desired range of 160 plus or minus 10 degrees, we are able to fit 5 standard deviations on either side of the mean. Calculating the CP, we get 170 minus 150 divided by 6 times 2.0, which comes to 1.67. For this process, our 6 standard deviation ruler is even shorter. Looking at the CP calculation as a question, can we fit the ruler within the range of the customer's tolerance? The answer is yes. In this case, we can fit the ruler not just once, but also 2/3 more. That is what the CP value of 1.67 implies. We have moved up another notch on our process capability scale. Let us now look at our 6 sigma capable coffee machine, Model D. This machine is able to produce coffee at an average temperature of 160 degrees with a standard deviation of 1.67 degrees. Within our desired range of 160 plus or minus 10, we are able to fit 6 standard deviations on either side of the mean. Calculating the CP, we get 170 minus 150 divided by 6 times 1.67, which comes to 2.0. For this process, our 6 standard deviation ruler is much shorter, half the length of the original ruler. Looking at the CP calculation as a question, can we fit the ruler within the range of the customer's tolerance? Yes. In this case, we can fit the ruler not just once, but twice. That is what the CP value of 2.0 implies.
Okay, I'm going to just halt the video at that point and understand that there's a measurement that we speak of now. We've been doing it all evening, okay? And now they're just expressing it that the upper spec limit and lower spec limit from the customer is not changing. What's changing is the average distance to the mean, or the standard deviation, keeps getting smaller and smaller. We're getting better and better, all right? The reason that he's painting the chart this direction is this is the way that you normally see control charts in production, is that it's a digital dashboard and the data will be running past you from left to right, okay? And they're able to redraw this on the fly. It's like a real live Excel looking at all the data, and they'll have alarms set, it can watch that the average doesn't change and things like that. That's why it's turned on its side. But what we've basically been noticing is that the sigmas keep getting smaller and smaller, so that what they're calling the capability of the process, the CP, it keeps going up, all right? So the minimum value of the capability needs to be 1. It needs to say that without any drift, absent of drift, that the span, the range from the upper spec to the lower spec is no smaller than 6 sigma, or conversely, that our process is narrow enough that 6 of our standard deviations is no greater than the range of the upper spec minus the lower spec. That's the range of that. So CP should be 1 or greater. If we start out with something less than 1, then that means that we're not even capable. That means our curve is very dispersed. Our curve is very dispersed. I'm kind of tracing out a very wide normal distribution, okay? Now, I just want to finish off. We grow this concept to a ratio, okay? where rather than just a simple capacity measurement, we include the concept of drift. Okay, and this video captures all of that in one video. I'm looking ahead here where he starts speaking about it.
Denoted by C subscript PK.
Okay, so we had the simple capability of the process, and now we have this other thing to differentiate it. Both of these can be used, but we're coming up with a more useful measure now. We're coming up with an index. It's based on what we just saw, but it takes drift into consideration.
CPK can be calculated using the formula shown. Think about this calculation also as a question, but as a two-part question. Each part of the question looks at how far the process mean is from one of the ends of the customer's tolerance range. For CP, we were trying to fit a 6 standard deviation ruler 1.33 times within the entire customer's tolerance range. 1.33 corresponds to 4 sigma. For CPK, we are trying to fit a 3 standard deviation ruler 1.33 times on each side of the process mean. If the process mean is closer to one of the edges of the range, we have less room on that side, so that side will limit our process capability. Calculating the CPK, we see that the upper and lower specifications and the standard deviation are the same as for our CP calculation. However, the process mean has shifted to 162 degrees. We can fit the 3 standard deviation ruler 1.6 times between 150 degrees and 162 degrees, but only 1.067 times between 170 degrees and 162 degrees. The CPK value is the smaller of these two numbers, or 1.067. An interesting point to note here is that the average of 1.6 and 1.067 works out to 1.33, which is our CP value. If the process were to be centered at 160 degrees, then both parts of our CPK calculation would work out to 1.33, and CPK would equal CP.
Okay, just to halt it there, don't let this equation, it's not as complex as it looks. I'll draw it graphically here in a second, okay? And all he said there was that if your process is not drifted, then CPK is equal to CP, all right? Okay, what he's talking about, we've already done it. I mean, I've actually shown all this, but there's a number. He's just putting a number to it now. Let me scroll down here a little bit. Okay, what he basically said was that equation that you're looking at, you're looking at which of the numbers is smaller. Let me show you this a different way, the way that we've been looking at it. Here's your curve, okay? And here's your target average, all right? And then our actual mean is drifted down from the average a little bit, like this. And the customer, I'm going to do symmetric. This is the target average. So the symmetric around there is here and here. Okay, so this is where we're trying to fit between, okay? And what he's doing, if you look at what the numbers are involved with this these are actually simple equations. It's very related to the simpler one that we just saw, but it just says, how far away is our mean from the lower spec? Let's just take that much of it. How far away is our mean, this is our active mean, to the lower spec versus how far is it away from the upper spec? That's all they're doing. They're seeing, what you're determining is which direction did our process drift toward. The smaller number here is going to indicate to which spec limit our process gravitated toward or skewed toward, drifted toward, to use the right word, okay? So if the number is smaller than this one, that means that we've drifted to the lower spec limit. If these are equal, if these two things are equal, that means we're still centered. That means that it never drifted, okay? If you look at it for a little while, you're going to see it's almost the same equation, but we're just looking for which direction this thing shifted in, okay? And this is accommodating the concept of Six Sigma, okay? It accommodates the drift that we allow for Six Sigma, which is 1.5, minus 1.5 to plus 1.5 drift, okay? That's what this is getting at. It's actually just mathematically expressing which spec limit, lower or upper, did we drift toward, and does 3 of our standard deviations still fit there? Remember, in Six Sigma, we had to be tight enough that when we drifted, that the acceptable levels of this stayed within the range if we drifted from minus 1.5 to 1.5, okay? So if you notice right here at the end, we're almost at the end of this video, and he's actually given us more of a view of how you see things in industry, where you see basically a bar graph running past us on a dashboard, and you can monitor things constantly, and you'll see let me do a quick screenshot of this, okay, so I can draw on it. Escape. Okay, so if I drop this in, I don't know why I came over here. If I drop this in as a visual here, I'll paint with green, okay? So here we have, this process is centered, okay? So this has been centered here just fine, okay? And then, see, the narrower we get, as we get to be very narrow like this, most of our points are right around the average, we're allowed to drift more, okay? Because we have more leeway down in the lower tails here. That's all that this is going through, okay? All right, with that said, I'm looking for any other comments here. I'm going to stick around. You might want to think about that a little bit if you've taken any notes and whatnot. You do want to understand the difference between when we do this calculation of the normal distribution using Excel, understand why we get a number when we're looking at minus 6 sigma. And then there's this concept out there, this huge global industry activity, if you will, or dimension or discipline of 6 sigma. And they go around touting this 3.4 parts per million, when we did the math originally, we found out that it was 2 parts per billion, okay? So I went through that specifically. It's not really in the book at all. It's a piece of practical advice or practical information for when you get into meetings regarding quality and somebody's shooting that around, and you can understand, I mean, they might not even understand that the process is allowed to drift, and that's what creates this other number, 3.4 parts per million. So that covers all the information for the final exam. It's going to be on this kind of information. You do need to, let me be clear about that. You do need to sit and listen to the videos. They're there for a purpose. They're pretty much the most precise or concise videos that I can have on there that augment what I've been giving you by drawing it, however painfully here in this drawing package of whatever this is. So it coincides with that, and the questions will be related between this lecture and the videos. The videos are augmenting that, okay? So I'll stick here for a few minutes. Is the final time on e-class, or is it one that we know? As I've always offered this as the final exam will be due by a certain due date. And I have to refresh that. I'm not sure who just asked that question. Cynthia, you asked me what is due. And when I go offline here, oh, that's Nick. Right now it's not timed. I'm going to I would like to have it timed, but I'm going to talk to the online people tomorrow and see if I can set it up to be timed. I have not found a way to do that. It's right now just set up for a due date, okay, which will be Friday or Saturday. I have the final paper. It's one or the other. The final paper and the final exam. One is due Friday, one is due Saturday. I made the due dates for the quizzes. Be very aware that there's these quizzes sitting out there. It's pretty much impossible for me to take information after the due dates because I get right into grading and I have to turn that in, I think by Tuesday or something like that. So I don't have much time to run around asking people that, you have completed this and you haven't completed that. I've tried it in the past and the ratio of work is like 10 parts of work for me for every 1 part of work on a student. So I really have to hold the schedule. I'll make it clearer by midnight tonight or tomorrow morning here as to when each is due. But I want to remind you that the quiz arrangement that I set up was open. It was not a timed thing, and I highly recommended people get that done in advance. You don't leave it all to the end. The quiz will probably take you some review and looking into to be able to answer the questions there. So watch out for the deadlines. I'm just going to take what I have, and there should be deposit points for all those on eClass. You should be able to find those. Okay. Good question there. And Cynthia, your earlier question was related. I think it was about. I'm going up there. I'm looking right now. You had asked that question. I'll be honest with you. I have to look. I forget which one I made. I talked about it in class one night, and I just have to look at it, and I'll send out an email to refresh just what I've said here. I'll just refresh everybody by email about clarity on that. But you pretty much want the quizzes finished earlier, so you don't have all this work stacking up for the end of the week. Okay. Any questions? Or questions 1A and B of the first 4. You're talking about the quizzes, Nick M? On the quizzes? Yeah. Can you refresh me? I'm not looking at it right now. I have to be honest. I have to be careful what I open here because I have the instructor version in there with the student version. I have answers in there. Just refresh me what the questions were. It's worth mentioning, probably. Yeah. Well, maybe I could. Let me just turn off my screen sharing for a sec. Go with the quiz. Okay, so we want to look at the Word doc, right? The Word doc here. Look that up. Okay. Why is it open? No, I'm trying to find out why. For some reason, it's not opening the file. Yeah. Now I see what you're asking. I just remember what the question was about. So come back over here. Okay, resharing my screen here. Okay, to do for which contract was scheduled? Yeah, yeah. I actually went over this in class pretty clearly one time. I alluded to it earlier, but I pretty much helped lay out what was going on there. Why in the schedule session, when we did the estimates using nominal numbers, why did it come out that some of the contracts were coming out a lot earlier? And there's an omission. I don't think I'm adding anything into this that I hadn't already written for the quiz, but there's a reason that there's a description in the student manual that you're given. Okay, so you can consider the student manual as a plant manager manual, really, which had an omission in it, and obviously was lacking a lot of information. That's why you're doing this report. You're adding in all this other information in there and whatever else. But it excuse me, it does have to do with Mod 4. It has to do with your experience in the timing of the schedule part of it, of the actual versus forecast time it would take to do any of the contracts. And this is pretty good that those of you that are able to have joined me here tonight, was, this is kind of very important information for having come tonight to understand that the way the quiz was set up, you can use a lot of that in your report. I was trying to pull out, in a way I had never done before, using the quizzes, some information that you want to put in your report, okay? So the plant manager manual didn't really help you out. There's a thing going on with that. There was an omission about schedule, okay? So that's what I was getting at with that question. So when you say Mod 4, yeah, I mean, it has to do with having gotten through Mod 4 and perhaps even finishing the Excel spreadsheets for the final report, where you can have 12 contracts fully analyzed for profitability and for schedule, okay? So it had to do with running Mod 4, but probably going back in there and completing 12 contracts as far as forecasting goes, all right? Okay. Let me know, was that helpful or not helpful? You still have a question? Yes, use the Mod 4 sandbox is there to do exactly this. This is how I've set up the course. I found that that leaves you the ability to go in there and run a bunch of contracts, pick on different kind of contracts to see why some were profitable and some weren't. And the second part of that question, there's certain aspects or characteristics of contracts that will exacerbate the omission, and some will underplay the omission of the manual. Okay, there's a certain type of contract that you would start categorizing. You'd say these kind of contracts you're going to end up with more of an underestimate of the time that it takes. And what you probably want to mention in there, I didn't put this in there directly, but to really provide reality to this whole thing is, why does this even matter? Well, if you aren't accounting for something that the contracts are taking less time than estimated, you're overestimating them, that means you're not going to bid on enough contracts, or you're going to bid on contracts, you're going to fail to bid on contracts that might have been most profitable when you thought you couldn't get them really done. When you really realize what's going on inside the operations, then you could have taken on more and better contracts. It's a very significant issue here. Yeah. So I'll post. I'll post this video. I don't think I have to post the, what do you call it? OneNote. The OneNote. I don't think I have to post the OneNote PDFs because they're in the video. All right. True. That's true. Old contracts are gone now. That was, but you have to run through some of the ones that you're offered. I forget who it was I was speaking to. I can't remember if I talked to somebody online with a phone or not. I think might have been the undergrad that's been essentially taking the course with you on the side. You all haven't met him, but he's basically taking this along with you. The idea of the course and using the simulation in the course is that you develop the Excel to get through Mod 4. For anybody that has hesitancy or has struggled to get through Mod 4, I haven't really had to say this in this course. Everybody's either gotten really close to it or gotten past the goal achieved mark on this, right? But that's why for some of you, you might be thinking, like, why do I have to go back in there? Well, the real thing that you would do at the factory would have been developing the tool as you go along, and that's how it was presented in the course, is that this tool is used to, if you want to think about it, you're out there 30 weeks. You're certainly not going to be let go for 30 weeks and not have any communications, until the very end. During almost every week, maybe sometimes for a while daily, you'd be calling back to the office and letting them know things, all right? And one of the things would be is the reason that you're really using the analytics from the Excel file just explain what's going on, substantiate it, that you're more than lucky that you're predicting. You're now characterizing production through looking at profitability and the schedule. Okay, so I wanted to cure any thought like, well, wait a minute, why do I have to go back and run that now? It's designed so that you build the analysis ahead of time, and that you do the figuring out of the operations in a controlled manner. That's what the intent of all this was. Okay, so to help you understand that. You need to run new ones to pick up all the information to fill out 12 contracts, although the original 5 are always there. So you can run through the 5 and pick up the numbers that you need to look at, what you thought it would take as far as schedule and what you thought the profitability would be versus the actual. Okay. Good questions. But I thought I'd lay out what the motivation was really there. This term, we had so few people, and despite that, everybody got through this fairly well. And Stephanie, I know you're still trying to get through there, but you got really close. So that if you were down $100,000 or something like that, even 10,000, that would be, kind of a signal. But you've been up, so you've almost figured it out. And I'm generally going to be around my computer fairly much this week. So if there's any other questions like this, I'm generally available. But I found this video that I offered tonight is very useful to understand just a little bit of a difference with the capacity measurement and the capacity index, the two different numbers. They're basically just applying the numbers that I went over tonight and other nights about this, applying them in real life. Okay. So as I said, I still see there's 5 others besides me, 6 still here. Free to leave at this point. Really enjoyed having class with you. Really was you all showed really good enthusiasm. I'm going to tell you straight up that it made it enjoyable for me for this course. And I think we adjusted the content to fit the 6-week schedule. Just make sure you get through this week, and I'll issue the final within probably 16 hours or so by noon tomorrow. So as I said, you're free to take off and leave me other questions and comments if you care to. I'll leave this on for a little while. The only thing is, some of you are checking out here, just remember to keep, in your final report, to keep the premise alive. Don't fall into a pattern of talking about Mod 4 or anything that like class academically oriented. You're speaking, remember, the idea here was to get value from writing a top level report back out, which is a big part of advancing in just put career advancement in there, not just getting promoted and raises and bonuses and things like that, but it's good for the business, right? It's good business, good for business. And the other comment is that remember you can use video speed controller when watching YouTube. I have had problems with it all of a sudden, as many other people in the community have also. What I have to keep doing is repairing it. For some reason, there was a change in YouTube, and it's blowing away the video speed recorder occasionally, so I have to kind of almost reload it when I need it, all right? So I just thought I'd mention that. Okay. I think we might have gotten all the questions there may have been. Feel free to just email me. I'm going to be on email tonight myself. I'll still be working tonight. I have things to do through the rest of the week. I'll be available. All right. So thanks for being here for the class and for the course. Very good. We'll talk to you soon. Bye now. That's I don't know if it's saving or not.